Alright guys, let's go ahead and get started on our client. So in this video, I'm going to put together a class inside of the BuzzMMO base infrastructure namespace, and then we're going to stub out our client, and if we have time, I'm also going to put together a console application that actually shows all of these components coming together. Even though the components won't have any implementation in them, we'll see how the classes interact and get a good sort of bird eye view of how this is going to work. I spent a lot of time putting this framework together, and I put it together for there are a handful of things that I really wanted to do. First of all, I needed it to be simple. Needed to be easily understandable, have very clear dependencies and very clear usages. Second priority was to make it testable. I really want the ability to be able to spool up an entire environment, both all the servers and all the clients running in memory in a process, not depending on Photon or networking at all. In addition, I also am starting to move towards the idea that a lot of things can be shared between the client and the server. Now, we're not going to do that in this video or in this part of this series, but we will go ahead and we'll write these classes out, and we'll write them out with the expectation that there might be a time in the future where we can actually replace some of their counterparts within the server itself, cleaning up our code substantially and all that fun stuff. Another big goal with this system is for it to be very flexible, because I want different kinds of players to be able to log in. I want the concept of having systems, and then the concept of a world, and the concept of counters and dashboards and admins and all that fun stuff. So I wanted to make sure that the entire client framework itself does not in any way impede the extensibility of how our protocol is going to fan out. So I make a lot of decisions with this to make it to introduce abstractions where necessary in order to increase the usage of this beyond just the concept of our systems, because we've been so focused on the system RPC framework that's easy to forget that we also are going to have to work with actors and zones and regions and counters and admin panels and all that fun stuff, and I don't want to at any point code myself into a corner and prevent us from extending it like that. We also have to realize that there are going to be a lot of different kind of clients, or potentially. We'll have Unity, obviously. We also may have clients that connect from console applications, from WPF applications, and even server applications. I mean, imagine having an online dashboard where you can connect in and all that fun stuff. And all those systems have different constraints and different ways we want to use them. But at the core abstractions that we put together need to be cognizant of what it is we might add in the future. So I spent a lot of time thinking about the interactions between these components, their dependencies, and extensibility points, and I came up with a solution that I think is pretty good between ease of use and how much it offers. Again, it's mostly pretty bare bones what we're going to do, to be honest. But we're going to establish a language for this framework, at least on the client side, and that's really important. So, all right, so we're going to start off by making just a class that I'll try to explain what it does and why we need it, and we're going to put that in our infrastructure namespace. And this class is going to be called the callback byte cache, and I'm also going to say tick1 because it's going to be a generic type. Of course, I'll remove the tick1 from the class itself, but the file right here, the callback byte cache, does have a tick1 in its file name. It is going to be a generic type, and we're going to have t callback type, and I'm going to add a generic type constraint of t callback type being a class. So what is this? What does this class do? Well, remember how we have these IRPC responses that we can return data from our server back to the client? We need some sort of way to deal with knowing when a message is sent from the client to the server and the server sends a response. We need to know a way to map. We have a way to map. What did I call this callback? byte cache. You know, a better name would be something like callback map. Or callback byte map. All right, I'm going to change that, and I'm also going to change the file name to callback byte map. And what it does is this class is only responsible for containing a sort of rolling list of callbacks and generating IDs based off of them. And we're going to use this because remember our MMO peer? Or actually, that's in our client context now, isn't it? Remember our system invoke ID? Where does that system invoke ID come from? What data structure do we use to contain the callbacks that a client needs to register so that when the server responds with something, we know which callback to invoke? Well, that's what this class does. Let's go ahead and write it out. Very short class. We're going to need 2 bits of information. We're going to need a private read-only T callback type array, and we'll call this callbacks. Then we need a private byte next callback ID. Now, next callback ID is not read-only, and that's important. Now we're going to create a constructor. Inside this constructor, I'm going to instantiate callbacks to a new array of callback type, passing in byte.maxValue as its as the size of the array, and then next callback ID I'll initialize to 0. We're going to have 2 methods. So I'm going to do the first method first, and it's going to be called it's public byte, and we're going to say register callback. It'll accept a T callback type of callback. What it's going to do is this method is simply going to register a new callback into our callbacks array and return the resulting index. We're first, however, going to make sure that we're not overwriting an existing callback. So I'm going to say if callbacks at next callback ID does not equal null, throw new invalid operation exception. And notice how using system appeared at the top. And I'm going to say callback blank already registered. And passing in next callback ID as the format string. Why do we need this? Well, our next callback ID is going to wrap around to 0 after 255 callbacks have been generated. And if it wraps around and those callbacks haven't been executed yet, it's going to throw an exception indicating that something has gone wrong. We could enter a loop that'll find the next callback ID that we can use. I don't want to do that quite yet because I want to get a feel for if 255 registered callbacks at a single time is valid. And I think it would be, because honestly, systems that return data are going to be the kind of systems that, just systems in general, don't get invoked a whole lot besides movement. And movement, we're not going to return data for performance reasons. But systems will be things like your inventory system or your quest system or what have you. And it's important that that we don't call them very often. Anyway, regardless. So we should never hit a point where we roll back our next callback ID and we hit a callback that hasn't been invoked yet. If that happens, that's probably a bug somewhere, and we should address it. And what do you do when you identify a case where it might be a bug that we should address? You throw an exception. Okay, the rest of the method is pretty straightforward. I'm going to say var callback ID equals next callback ID. Then I'm going to do something a little weird. I'm going to say unchecked next callback ID plus plus. So the unchecked keyword, I'm entering a block, and then I'm incrementing next callback ID. What does this do? Well, the default behavior of most number operations in C# is that if there's ever an overflow, it will throw an exception and it won't wrap back around. So for example, if we hit 255 and we try to add 1 to it, it won't wrap around to 0. Instead, it'll throw a exception. Because we explicitly want next callback ID to wrap back around to 0 when we increment it, we're going to make this unchecked. Okay, then I'm going to say underscore callbacks at callback ID equals callback, and then I'm going to say return callback. Or sorry, return callback ID, derp, so that we know what to send to the server. Then I'm going to say public tcall, so another method. and it's going to be called, I don't know, something like get callback. And we're going to have a byte callback ID. Then I'm going to say if callbacks at callback ID equals none, throw new invalid operation exception. Callback blank was not registered, or is not registered, or has already been invoked. All right. Then I'm going to say var item, or sorry, var callback equals callbacks at callback ID. Then I'm going to say callbacks at callback ID equals null, and I'm going to say return callback. Return callback, not callback ID. And that's our callback byte map. Pretty straightforward. I'm putting it in infrastructure kind of as a precursor of me fixing up the server code to reuse a lot of the client code. And also, we need this class because we might want different kinds of transports that we might want to create, and they'll all need this functionality. And I find adding this functionality to an existing class is really gross, and I find putting it into its own class cleans up the code a lot. So that's our callback byte map. Not too exciting. Not going to be using it quite yet, but we will be here shortly. All right, let's go ahead and stub out our client. So I came up with an order of how I want to stub out the client based on how the usage is going to work with it. And so what I'm going to do is I'm going to go through all of the client stuff, stub it out, just write up the class names and do all that fun stuff, and we'll go from there. So in the client, I'm going to create a namespace, and it's going to be called infrastructure. Not surprisingly, this is probably something that will live in the base infrastructure namespace at some point. Inside of the infrastructure namespace, I'm going to create an interface, and it is going to be called iClient Transport. Now, what does the iClient Transport do? Well, really, all it does is it's responsible for sending operations to the server. So I'm going to say void send operation code, which comes from base infrastructure code, dictionary, which comes from collections generic, byte and object, parameters. Then I'm going to create another overload, send operation, of operation code, dictionary of byte and object, parameters, and then action, which brings in system, of operation code and dictionary byte of object. And then I'm going to call this, I don't know what I want to call this, on response maybe. And there we go. All right, that's our client transport. It's capable of sending operations, and it has an overload for retrieving an on response in the form of a delegate, which accepts an operation code and a dictionary byte and object. All right. Now that we have our iClient transport, let's move on to our transport base class. Now, our transport base class is interesting because it's kind of this in-between place. It's in this in-between place of being a specific implementation of iClient transport, but it doesn't actually do any transport. It's really just a convenience class that makes implementing an iClient transport easier. It also introduces the concept of what I call event reader modules. We'll talk about those here shortly. So inside of infrastructure, I'm going to add a new class, and it's going to be called transport base. Not surprisingly, transport base will be abstract. So public abstract class transport base. What I'm going to do is when I write out these stubs, I'm going to write out the stubs of all the methods, all the classes, and all of the private fields. So what private fields do we need in our transport base? Well, first of all, we do need our callback byte cache or callback byte map. Now, what do we pass into the generic parameter? I realized I didn't actually specify what it is we pass in here. What we pass in here is a delegate. So things are going to look a little weird here. So watch this. I'm going to pass an action of type operation code and dictionary of type byte and object, and I'm going to call this callbacks. Yeah, it looks a little ugly. You might be having flashbacks of the STL or something if you're a C++ developer, but it's pretty straightforward. I mean, we have this callback map byte map type, and then we pass in a delegate as a generic parameter, and the delegate accepts a operation code in a dictionary byte and object. Now, people might be asking me, why am I relying on action instead of making my own delegate type? And you're right, I could. I could make a delegate type that handles operation code and dictionary byte and object, but I've just gotten so used to using action and func. I find them more readable to immediately see what parameter types are expected of a delegate in line with where I use that delegate. All right. Now we're going to do some more delegate craziness. Private read-only of action of event code and dictionary of byte object array. We're going to call this event handlers. Okay, so what's going on here? Well, we have an action delegate type right here, which is a method that will accept an event code and a dictionary, the dictionary being of type byte and object, and we have an array of them. And that's what our event handlers field is. Again, a little heavy on the syntax. You know, maybe type defs would be really cool to have in C#, but we don't have them. So, yeah. Anyway, I did forget one really important thing that people might have already picked up on. I forgot to have transport base actually implement iClient transport. So let's do that. Up here, we'll have public abstract class transport base implementing iClient transport. I won't worry about implementing the methods yet because we're just going to go through this entire class. All right, first thing we need is a constructor. We're going to make it protected. I like making constructors protected in abstract classes. Okay, so we have a protected constructor. It doesn't do anything yet. Remember, these are all stubs. We're going to have a public void add event reader. Event reader module event reader. Now, I might be saying, well, where does event reader module come from? It's actually going to be a nested interface in transport base, and we'll define it at the bottom of the class. Next up, we need our public void send operation. Send operation will have an operation code, dictionary of byte and object, parameters. Then we're going to have our send operation code dictionary of byte and object. Apparently I can't type anymore. Parameters action of operation code dictionary byte object on response, I think I called it. Anyway, these are these two methods implement the iClient transport interface, and we're going to leave them blank. Then we're going to have a couple protected methods. We're going to have a protected void handle system callback method that'll take in an operation code and a dictionary of byte and object. We're going to call these parameters. And we're going to have a protected void handle event method that'll take in an event code, dictionary of byte and object, parameters. Then we're going to have a protected abstract void send operation internal, operation code, dictionary of byte object, parameters. Oops, no implementation because it's abstract. All right, so I hope you guys are getting more of a feel of how transport base is going to help us out. Basically, it handles the callbacks. It handles registering new modules, what I call them for event handlers, and then it basically uses this one method right down here, which will be implemented in the base class to actually perform the network operation or the in-memory operation if we want to. Or the carrier pigeon operation. I mean, we could write an implementation of transport base. All it needs to do is provide an implementation of send operation internal, and it could just package up that dictionary on a piece of paper, or wrap it around a pigeon, and send it off to its destination. I mean, that's the whole point of abstraction here. You can kind of think of the transport base class really being a example of the template method pattern, if you're familiar with that. Okay, we have two more things to do here. And that is, we need to create an interface and a class. So I'm going to say public interface iEvent reader module. Now this might be the first time you have seen a nested interface or nested type. And yes, you can nest arbitrarily as many types as you want in a class. And what this allows us to do is our concept of iEvent reader module is so specific to the transport base and not used anywhere else that I felt it made more sense to put it into the class itself. If it was more there'd be two instances that I would have that I would have put the iEvent reader module into a different file. Two instances. Either A, iEvent reader module is intended to be used by anything other than transport base, or B, the transport base is such a large system that it spans multiple objects, and I might as well put it into its own namespace. None of those two conditions are met, so I'm just going to make it a nested interface. Now, this nested interface is going to have one method. It's going to be an IEnumerable of event reader module registration. Get registration. So the purpose of the iEvent reader module is that a implementing class can return multiple event reader module registrations. Now, what are event reader module registrations? Well, that's going to be another class here. So after we define that interface, I'm going to say public class event reader module registration. It's going to have two properties: public event code, public action of event data, event code, dictionary of byte and object, and we're going to call this action, get private set, and it's going to have a constructor, event reader module registration, event code, and action of event code, dictionary, byte, object, action. In addition to that, I'm going to actually cheat and implement this constructor because it's so ridiculously, stupidly trivial. I'm simply going to say code equals code and action equals action. Remember to make these uppercase so that you are referring to the properties and not to the parameters. Anyway, again, the event reader module registration is simply a data object that describes a single operation that a particular event reader is capable of handling. An iEvent reader module is nothing more than a way to retrieve all of the events that a particular module is capable of handling. This whole concept of the event reader actually took me a while to come up. As obvious as it might look or seem now, if you can kind of see where I'm going with this whole system, it was actually kind of difficult to put together, or at least come up with. But what it gives us is it gives us the flexibility of the transport base, not knowing anything about actors, world zones, systems, dashboards, counters, and having this be kind of like a composed object, an object that is composed from other objects that actually have their particular responsibilities embedded within them. Either way, that's about it for our transport base. All right, moving on. Let's go ahead and stub out our Photon client transport. Actually, I don't like the name transport base. I just realized I don't like that name. I'm going to name this to I'm going to name this to client transport base. I don't know why I said transport base. It's the client transport base. All right, so rename that. You'll rename the class, you'll rename the constructor, and you'll rename the file. Or hit Control-RR and rename it through a sharper. All right, so inside of our infrastructure namespace, we're going to go ahead and add our Photon client transport. Now, this is, not surprisingly, the Photon specific code of how our transport layer is going to work. He is going to inherit from client transport base, and he is going to implement iPhoton peer listener. Now, iPhoton peer listener is an interface that's given to us by Photon itself, and it's what it does is it allows us to receive notifications over the network, basically. Okay, so inside of this, I'm not going to use ReSharper to implement iPhoton peer listener. Reason for that, we'll see very shortly a actual use case of doing explicit implementation, which is a really cool feature of C#, which most people don't know about or use. The first thing I'm going to do is I'm going to say private read-only photon peer underscore peer. Then I'm going to create a constructor. And in addition to that, I'm also going to say public event. Actually, no. This class is actually going to be... I'll include it. I'll include it. I'll be removing it later, but that's fine. I'll be doing a slightly better implementation instead of having a... But we're going to have a public event action of status code status changed. Okay. So we have photon client transport. Let's go ahead and do public void connect, string server address, string application. This will just connect the photon peer. We'll have a public void disconnect. Dare you to guess what that method does. We'll also have a public void service method. Now the service method is going to just delegate to the peer. And by delegating to the peer, it will tell it to update its stuff, like process new events and send operations and all that fun stuff. Then we're going to have a protected override void send operation internal. And I'm also going to get rid of these namespace qualifiers and import BuzzMMO infrastructure as well as systems collections generic. And we'll be leaving that method blank as well. Now let's go ahead and implement the iPhoton peer listener. I don't know if you guys have ever seen this syntax before, so I'll talk about it and describe to you why it's valuable. So the iPhoton peer listener has 4 methods that we have to implement: debug return, on operation response, on event, and on status changed. Let's go ahead and write on event first. So I'm going to say void iPhoton peer listener dot on event data event data. Then I'm going to say void iPhoton peer listener dot on operation response, having operation response. Then I'm going to say void iPhoton peer listener dot debug return, passing in a debug level and a string message. And then we're going to have a void iPhoton peer listener dot on status changed with a status code. All right. So now you see that I've implemented these 4 methods. Our error at the top of the file goes away because we fulfilled the iPhoton peer listener contract. So what's up with the syntax? Well, this is called explicit implementation. Or, yes, explicit implementation. What it means is, if you're familiar with C++, it's actually very similar to privately inheriting a class. Basically, these methods are wired up into the iPhoton peer listener just as we would see with implicit implementation, which is what you guys are used to seeing. For example, if we move over to our client transport base, look at our send operation methods. These methods come from iClient transport. Notice on the left-hand side, ReSharper is telling me that they implement methods from iClient transport. But you'll notice that they're just public void methods, or they're public methods that match the signature of the method on the iClient transport. This is implicit implementation. This is explicit implementation. The awesome thing about explicit implementation is that these methods are private. Because these methods are private, there's no way to invoke them on any Photon client transports without first casting it to an iPhoton peer listener. That's a good thing, because it means that Photon can still invoke these methods, because all Photon cares about is that we implement iPhoton peer listener, and that's what it knows us as. But the rest of the code is going to know us as a Photon client transport, and we're not going to be allowed to invoke these methods directly. I kind of like that because I don't want things to get confusing with how this particular class has been constructed. All right, so that's our Photon client transport. Basically, we have our transport hierarchy. right here. Our iClient transport is basically what everything else in the system is going to use. Our client transport base is going to be a convenience class for making new kinds of transports easily. And our Photon client transport is an implementation specific to Photon. This is where in-memory happens, because when we make an in-memory transport, we're going to inherit from the client transport base, which is really cool. Okay, so that's it for the client infrastructure. Let's move on to the implementation of our systems. So I'm going to create another namespace in client, and I'm going to call it systems. Inside of systems, I'm going to go ahead and start writing some classes. I'm going to start off with an interface, and it's going to be iSystemFactory. Now, what's iSystemFactory responsible for? Well, an iSystemFactory is simply responsible for instantiating a system in some sort of way. Now, the reason why I have this as an interface is because depending on where our client is running, there might be different ways to instantiate objects. For example, you might be running in WPF, and you might want to use AutoFac to instantiate your systems like we do with the server. Or you might be in Unity, and you have to create new game objects and add your systems as components. So basically, the system factory is just a way to abstract away the concept of instantiating a system so that our client framework can work on a variety of different platforms in a variety of different circumstances. It's going to have a single method, which is going to return an iSystem base, which we get from base infrastructure, and it's going to be called createSystem. Okay, so the parameters are going to be a little funky. We're going to receive a type, and the type is going to be of the interface type that we need to instantiate. I'll go, yeah. No, we're going to do interface type. The second parameter is going to be a func delegate that accepts a type and returns an object, and it's going to be called proxy factory. And the final parameter is going to be an out type concrete type. I spent a lot of time thinking about this method, and a lot of time trying to identify how to create this in the most flexible way without sacrificing or without requiring a lot of additional code to make different components. And this is what I came up with. So basically, the system factory is going to receive an interface type. So let's say the server instantiates a login system. It's going to tell the client to instantiate an iLogin system client. That type is then going to be passed into the system factory. And the system factory is then going to figure out which concrete type matches that interface type. It's going to instantiate it, and then it's going to return it. The second parameter is a proxy factory. Now, why do I need this? Well, in my wanting to decrease dependencies and increase the readability and understandability of the code, I decided that the class that contains all of our systems is not going to have a concept of the system type registry. Therefore, when the server tells the client to instantiate an iPlayer login or login client, the object that's responsible for understanding the concrete types is going to be the system factory. So the first parameter to the proxy factory delegate is going to be the server component type. And then it's going to return an object that represents the proxy. Then we have the out type concrete type. And what that's responsible for is it's responsible for telling the thing that invoked iSystemFactory what the concrete type of that system is for its own purposes. So the great thing about doing it this way is that, well, for one, we could support dynamic proxies for systems themselves, creating basically more testable code. And in addition, we can support more complex inheritance hierarchies within our types themselves. So basically what I'm saying is that instead of the client systems instantiating or telling the system factory to create a system, receiving an iSystem base, and then invoking .getType to identify its concrete type, I would rather the system factory itself explicitly do that, because the .getType isn't a reliable method and may change depending on what you're doing with dynamic proxies and all that fun stuff. So anyway, that's our system factory. So let's go ahead and move on to our iSystems operation writer. Under systems, the system's in the namespace, I'm going to create a new interface called iSystems operation writer. This interface is going to have 4 methods. We're going to have void invoke method, mapped method, method object arguments. We're going to have another invoke method, mapped method object arguments action RPC response on response. Then we're going to have a void create system, mapped component, interface component, and a void destroy system, mapped component, interface component. So what is the iSystems operation writer? Well, this class is responsible for it's basically the other part of the events where we have our add system, our remove system, and invoke method on system. It's basically the counterpart to that. The iSystems operation writer will be invoked by the server proxy, and it'll tell the server that something needs to happen. So the iSystems operation writer will perform the actual serialization of the dictionary, and then pass that serialized data into the transport, and the transport passes it to Photon, and then Photon passes it to the server, and so on. And then we also have create and destroy system. We're actually not going to be using either of these methods. We're not going to be using them because this is sort of a precursor to me having this having a share code between the server and the client frameworks. I just put them in there to remind myself of that and to ensure I don't code myself into a corner anywhere. All right, let's move on to the client systems class. Now the client systems class is going to be pretty big. It's responsible for handling our systems. So we're going to call this client systems, which, yes, there is a class called client systems in the server. Client systems will implement iDisposable. Then we're going to have a private read-only iSystem factory. We're going to have a private read-only iSystem operation writer. We're going to have a private read-only iSystem base array of systems by interface ID. And we're going to have a private read-only dictionary of type and system information called concrete type to info. Then we're going to have a public component map with a public getter and a private setter. Next up, we're going to have a public constructor. The constructor will take in a component map, a iSystem factory, and an iSystem operation writer. Next up, we're going to have a public void create method that takes in a mapped component, interface component type. So in this case, it'll be a client interface component type. So you'll invoke create and you'll pass in something like, create iLogin system client or something. Then we're going to have a private object create proxy for type other interface component type as the parameter. Then we're going to have a public void destroy. Destroy will take in a mapped component, interface component. We're also going to have a public iSystemBase get by interface ID with the byte interface ID. Then we're going to have a couple more methods. Like I said, this is a big one. We're going to have a public T concrete type, or public T concrete type get T concrete type with a generic type constraint of it being a class and iSystemBase. Then we're going to have a public bool try get T concrete type out T concrete type value, where T concrete type is a class and it implements iSystemBase. Then we have a public bool contains, and we have T concrete type return, or yeah, I got ahead of myself there. It is such a simple method. I really wanted to get that in, but anyway, we'll also need to implement our dispose. So public void dispose. And yeah, I think that's it for the methods. Now let's go ahead and write our two internal classes, our two private classes. So I'm going to say private class, what did I call that thing? System information. And it's going to be a public mapped component interface type, get private set, and a public iSystemBase system instance, get private set. We're going to have a constructor, and the constructor is just going to retrieve both those values. So it's going to get a mapped component interface type and an iSystemBase system instance, with interface type equaling interface type and system instance equals system instance. Then we need our private class, and we're going to call this proxy interceptor, which will implement iInterceptor. Which this won't work yet because we haven't added a reference to castle. But once we add a reference to castle.core through NuGet, this will stop, breaking. The proxy interceptor is going to have a private read-only mapped component server interface, other, or how about proxy interface component, and a private read-only iSystem operation writer. It's going to have a public constructor that just does those two things. So I'll just go ahead and implement the constructor entirely. Mapped component, proxy interface component, and iSystem operation writer. And then finally, it's also going to have a public void intercept method that takes in an invocation. INVOCATION invocation. Which also won't, this will also throw an error because we don't have castle core yet. Alright, so that is our client systems class. So we'll just need to go through this line by, or method by method, and implement it. Most of these methods are going to be pretty straightforward though. Actually, virtually all of them will be. All right, let's go ahead and do our systems. Let's think here. Yeah. I guess we can go ahead and do that. Maybe. Okay, let's go ahead and do our systems operation writer. So under systems, I'm going to create a class called systems operation writer, which will implement systems operation writer. And this class will be responsible for actually serializing down the requests that our systems make. So I'm going to say private read-only iSerializer, which comes from base infrastructure, _serializer. Private read-only iClient transport. We're gonna have a public systems operation writer that takes an serializer, and an client transport. Then we're gonna have a public void invoke method. Is that what I called it? Yeah. Invoke method, mapped method, object arguments. We're going to have another public void invoke method, mapped method, object arguments, action of IRPC response on response. We're also going to have a public void create system, map component, interface component. We'll also have a public void destroy system, mapped component, interface component. Let's see here. We're also going to have a weird one. We'll talk about this method a lot more when we write it. We're going to have it's going to be a private. It's going to return an action of operation code and dictionary, which comes from systems collection generic, byte object, and it's going to be called parse response, and it's going to accept an action of IRPC response on response. So yes, this method will be returning an overload, or a delegate. It'll be kind of fun to put together. But basically what this is responsible for is remember how our iClient transport, how it the callback is a delegate that takes an operation code and a dictionary byte of object. Well, we need to be able to convert that into a action of IRPC response, because that's what the systems operation writer expects. So we're basically converting it at the transport layer up to a more abstract level. So this is where we deserialize the response, by the way. Then we're also going to have a private void set parameters of dictionary, byte, and object. Parameters, mapped method, and object arguments. And that is our systems operation writer. Again, it's all stubbed out. All right, let's go ahead and look at our the first factory that we're going to make. So up here in our systems namespace, I'm going to create a activator system factory. So I'm going to call this activator system factory tick1, and it'll have a single generic parameter of t system base. It'll also implement iSystem factory. It's going to have a private read-only system type registry called system type registry. It'll also have a private read-only action of t-system base in its system. It's going to have a public constructor of activator system factory, which will take in a system type registry, also an action of t-system base in its system. And then it's going to have a single method, public iSystem base, create system, type, what did I call these parameters? Interface type, proxy factory type. All right, type, interface type, action of type and object, proxy factory, and out type, concrete type. And it's a func of type action, derp. Alrighty, and the last class that we are going to implement is going to be, under the systems namespace, it's going to be a systems event reader. So the systems event reader is responsible for reading in events from the transport layer and dispatching them to our client systems. So it's going to inherit from or implement client transport base dot I event reader module. It's going to have a private read-only serializer, and a private read-only client systems, and we're going to call this systems. Then it's going to have a public constructor. It takes in a serializer and a client system systems. And then it's going to have a public IEnumerable of client transport base dot event reader module registration, and it'll be, what is it called? Get registrations. Then it's going to have a private void invoke method on system event that takes an event code, and a dictionary byte object parameters. We're going to be writing a handful of these private void methods that take in the same parameters. So I'm just going to take the whole parameter list and hit Control-C, get it on my clipboard. So I'm going to say private void add system event, paste. Private void remove system event, paste. And private void sync systems component map, paste. All right. So as you see, again, this is the sort of module that's going to plug into our transport layer, and it's going to kind of decide what to do with our client systems when we receive a message from the server. And that's really it. So, yeah, stuff and things. I guess I can go ahead and we'll do that in the next video here. So we got the stub out, and this is what it looks like. If you want, you might want to add throw new not implemented exceptions to all these methods. I forgot to do that. That way, you won't accidentally miss implementing a method instead of just leaving it blank. So if you want to add throw new not, just go through all the files and do that. But either way, this is pretty much the structure of our client systems framework. So when we go in to add things like zones and actors and stuff, obviously we're going to have a different namespace for that that'll also plug in to our client transport. So you kind of see how client transport sort of sits outside of everything. You can plug into it by creating these iEvent reader modules, and you can tell it to do things by telling it to send an operation, as well as being able to receive a response. But yeah. Everything else is just based off that. Our client systems receives a system operation writer. A system operation writer receives the transport. So it's a very sensical sort of hierarchy of how these objects interrelate. But I think that just about wraps this video up. And we'll see you guys in the next one.